Okay. Whoops. Sorry, I gotta make this full screen. All right. So we left off looking at this idea of the volumes and capacities. Here's a concept to consider. So, anatomic dead space. This is really, the dead is referring to doesn't participate in gas exchange. All right, that's what the dead means here. So anatomic dead space is really basically the space or volume of your conducting division. So all that, right, all those tubes are filled with air, but none of that air is currently being exchanged. So if we go back here, there's a certain amount of each of these volumes which is just filling these tubes. Well, it turns out, believe it or not, these tubes are actually, while they're the majority of what you can see, and they look really large, they don't really hold a whole lot, which is good news for us, right? So typically, your anatomic dead space is about 150 milliliters. Now, note, you can, hold up to 6 liters. So 150 is a trivial amount to give up, right? The alveolar dead space, this is a problem. All right, so alveolar dead space, because the alveoli are supposed to be participating in gas exchange in the part of the respiratory division, they would, if you've lost some alveoli because of disease, right, then you have to, how much are you losing? How much are you giving up here? So then total dead space is really both of these together. Air not being used in exchange. All right, so you add the anatomic and the alveolar, and you get the total dead space. So in a healthy person, right, anatomic dead space and total dead space are equal. In a person with disease, right, then the total dead space is greater than the anatomic dead space. All right, so here we look at control of this ventilation and how do we get, we meet the needs of the body. Well, that's of course going to be done through the brain, because the brain is a controller, right? So rate would be the number of breaths per minute to meet your needs, right? Normal breathing is involuntary, right? Yeah, you don't think about this. It's like every 2 seconds in, 3 seconds out, 2 seconds in, 3 seconds out. That's a normal at-rest ventilation or breathing rate, and that would end up being about 12 to 15 breaths per minute. So this continues even when you're unconscious. Yeah, you can fall asleep and feel confident that you're going to keep on living, right? But you already knew this, so this is not really new information to you. All right? Now, of course, the respiratory muscles can be controlled voluntarily. You can choose to hold your breath. You can breathe faster. All right? But ultimately, you can't keep that up. And that's why your kids can't, hold their breath until they die. Because your body's going to take over, specifically your brainstem, when you have too radical a change in the amount of carbon dioxide or oxygen, your blood gases, and of course the pH directly related to the amount of carbon dioxide. So I say here, or your book says here, what do each of these things do? Well, you have a medullatory respiratory center, and of course you have a pontine or pons has some influence on this too. So this one really talks to this one, but your medullatory center then consists of these ventral and dorsal groups. We don't have any models that show this in lab, and I've never asked this on a test, but they do differ in their control. So these are groups of neurons held within these areas. And so these are the controllers right here. All right. Then these are the sensors, right? The aortic bodies and the carotid bodies. These are very important. And they are also going to work with these cortical areas of the brain, these other areas in the brain that we're going to see that aren't mentioned on this slide. Okay, so aortic and carotid. So next to those baroreceptors are chemoreceptors. And we mentioned this back in the chapter on cardiovascular. The hypothalamus, of course, you change your breathing rate if temperature changes. You change your breathing rate if you're in different emotional states. So the hypothalamus does influence. It is wired to this. And we said that you can voluntarily control, so cortical areas can also affect this. Believe it or not, right before you even get ready to start working out or exercising, increasing movement, you'll start with a greater heart rate and a faster breathing rate, even before you need this. And this is done because proprioceptors, right, these position sensors in your joints, will start sending action potentials up to this respiratory center up here. And then, of course, you can get reflexes, and you also have the Herring-Bowers or the inflation reflex too, that affect breathing. All right. So these respiratory areas, and here we see it in a cartoon, right? This pons, the rounded part, consists of this pneumotaxic and this apnoistic center. And then here's the ventral, of course, and the dorsal groups. They're named for quadrupeds. It's just the way it works. And then we're seeing this. So these talk to this, right? And then, so pons talks to and modifies the medulla, and then the medulla is telling all these muscles what to do, all right? So they control your breathing when you inhale and exhale, and they adjust how often you do this, and they influence then these additional or accessory muscles for the depth to meet your body's needs. So when we see an increase, right, when we tap into your inspiratory reserve volume or your expiratory reserve volume, that's this group telling muscles out here in the thoracic cavity or in the abdominal area that you've got to change things because the body has a greater demand. All right. So the dorsal respiratory group back here is a constant breathing rhythm, stimulates diaphragm and intercostals. That's its job, and you see it moving here. All right. The ventral group is really the forced, so they affect different aspects of breathing. All right. And then the pontine, which is pontine, is the apnoistic, and that stimulates the dorsal group, and the pneumotaxic inhibits it. All right, so factors affecting your rate and depth of breathing. All right, so again, brainstem is controlling this, but it needs input, these sensors. So we looked at the peripheral chemoreceptors, right, the aortic and the carotids, and then we'll also have some central ones. And I mentioned down here, of course, as I sit on that table that began this, that the hypothalamus and limbic system, because of emotions, really influences. So, and this is all about meeting your body's needs. And how do you know what the body needs? So it turns out what these chemoreceptors are monitoring is amounts or concentration. But we identify this by this term partial pressure. So we're not really counting, as we would for concentration, all the carbon dioxide or oxygen molecules. We are saying that there's so many of them here that they influence this amount of pressure. So please think of partial pressures as concentrations. And you already realize that, again, concentrations going up and down influence diffusion. So we want to maintain these concentrations or your blood gases, all right? And these are measured in millimeters of mercury. So because they are pressures, but they really are amounts, all right? And we want to remember that carbon dioxide will, right, become water when combines with water, becomes carbonic acid, and carbonic acid then produces hydrogen ions and, of course, bicarbonate ions. So when carbon dioxide increases in the blood or cerebrospinal fluid, then we increase hydrogen ions and we decrease pH. And you must remember this relationship. This is a very important to get what happens here. All right, so arterial concentrations of hydrogen ions are due to other metabolic processes. So this is also going to influence this, and that's why later on when we go into acid-base balance, and I said the lungs are involved in acid-base balance, that if you have another source of hydrogen ions, and this would be from metabolism, that dump it into the blood, this will trigger faster, deeper breathing to get rid of the acids. All right? And then the partial pressure of oxygen, and this, right, we're looking at, which it has to be low for the chemoreceptors to respond. So high carbon dioxide, high hydrogen, we get a response. Low oxygen, we get a response. All right, and remember, chemoreceptors sense the dissolved oxygen, not that with hemoglobin. So just to note, there's a certain amount dissolved. All right, so changes in the cerebrospinal fluid. How do these sensors affect breathing? So if you increase carbon dioxide and you therefore increase hydrogen ion concentration and decrease the pH, this will stimulate these central chemoreceptors. And then impulses travel from the respiratory center to the diaphragm, and contraction occurs because of this. So if you have this situation, you are going to breathe faster and deeper. All right? changes in the blood. So these arterial or peripheral chemoreceptors. Again, increased carbon dioxide, increased hydrogen concentration, decreased pH, or decrease, right, oxygen concentration will stimulate these ones. And again, you're going to get contraction of muscles. You're going to get faster and deeper breathing. And I said the opposite happens as well. You can therefore increase or decrease breathing based on this, right, these sensors to match what your body needs. All right, we're going to skip the what do you know and move into gas exchange. Yeah, so now we've got all this idea of how we breathe and how we change our breathing. So let's look at getting the oxygen actually into the blood, because we've talked about it being in the blood here for these sensors, but how did it actually move? All right, so this gas exchange between the atmosphere and blood, right, and here we go, the pulmonary capillaries, is known as external respiration. So because it's the outside world coming in, right? We know Boyle's law explains the movement, but what do we need to know about these gases? So first of all, the gases are independent. So what carbon dioxide is doing, what oxygen is doing, what nitrogen is doing doesn't really influence each other. But collectively, they all participate. They all are part of the atmosphere, so they all comprise this, right, total atmospheric pressure. So this is just a breakdown of what our atmosphere is composed of, and here would be the pressures that result from each of these gases. All right? So again, independent, Dalton's law says they exert their own pressure or partial pressure. So what, again, oxygen is doing does not affect what carbon dioxide is doing, and nitrogen and so forth. All right? So by the time the air passes through the conducting division, so all through the trachea, bronchi, and down into, right, these terminal bronchioles, here's what has happened. Of course, our composition is declined a little bit for oxygen because it's been mixing with the air that's deoxygenated, that's already in the tubes, and humidity and carbon dioxide has increased in there. So again, just remarking, you don't have to know these for me. These are just to give you reference so you understand that these are actual physical characteristics. So gases mix, and therefore by the time you get to the alveoli, you have about 104. So when in the alveoli, we have our partial pressure of oxygen is about 104. Our carbon dioxide is somewhere around 47. How do we get them into the blood, a liquid? Well, so we're going from, again, a gaseous state to a liquid state, and we have to dissolve the gases. So Henry's law states that, right, how hard you push your partial pressure, which we have a lot of pressure behind oxygen, and we have a pretty good amount of carbon dioxide pressure, and the solubility. So this is a characteristic inherent to the gases. So let me pause here a minute and explain. This is why nitrogen, which is 569, there isn't a lot of it found in your blood because it does not dissolve. Its solubility, or the ability to dissolve, is so low that only very, very, very little amounts of nitrogen actually enter in this process. Oxygen's is better, but not great, and carbon dioxide is really the best. And of course, this is why we carbonate your beverages, right? I mean, and don't use oxygen, which we have plenty of. So carbon dissolves or goes into solution better than oxygen does. All right, so optimizing this exchange, we have to match the ventilation, right, the movement of this air in and out, and the perfusion, the movement of the blood to the pulmonary capillaries. The flow is, of course, controlled by that diameter of these tubes, which is affected by partial pressures and pH. So we want to take a look at how these all work together. The respiratory membrane we've already mentioned is absolutely designed for. So here's our gases from the atmosphere here in the alveoli. Here's where I want to get the oxygen and carbon dioxide. Here's plasma surrounding this blood cell. So absolutely designed for simple diffusion. What does diffusion depend upon? You might recall that it's the distance the gas has to travel. It's the temperature it's at. It's the concentration. That's the big deal, okay? Because hopefully in a healthy person, distance doesn't change. But this, of course, is what is going to cause death in many people that accumulate fluids or scar tissue in their lungs. So, but you, again, the biggest change is going to be in the concentrations of these gases. All right? So surface area, right? Partial pressure difference, concentration, solubility. This is really what we are looking at when we talk about how quickly will you diffuse. All right? And we'll pick up the rest of this on the next